Good afternoon. This is Brian Winkle. I'm the director of Semiote, and we're privileged today to have Erich McAlister at Fort Lewis College in beautiful Durango, Colorado. Erich's been an enthusiast for using the software Insightmaker, and in this case, to enhance his understanding in the first ODE course. Many of us find particular pieces of software, we're drawn to it, we're attracted to its features, we learn how to use it, and some of us share it. Sometimes we just kind of keep it to ourselves and our students. But we're really privileged. In the first session, we had Sami Kandarian talking about Wikipedia, a wiki model software that he developed. In this case, Erich is going to be talking to us about a freely available magical piece of software called Insightmaker with lots of illustrations. And he's going to tell us about his interest and his expectations for that, especially during this semester of his sabbatical. So I'm going to turn it over to Erich and encourage you to ask questions. And if he can answer them on the fly, that's fine. If not, he will get to them. So Erich, you're on.
All right. So first of all, I just want to thank Brian and Semiote for organizing these sessions. I think a lot of times when we're talking about teaching and the things that we do when we're teaching, the outlets that we have are really limiting. So the fact that we have this the opportunity to have a 90-minute session that's going to be published elsewhere is really, I think, empowering for the profession of teaching. So I'm going to be talking about using this software called Insightmaker, and you can go to insightmaker.com. That's where it is, and it's a pretty low entry thing. There's no downloads. You can open it up and say start building insights. So the first thing, just as an outline for the talk, so we're going to talk about just, okay, what is this stop flow modeling? And some of you might be familiar with this terminology, some of you might not. If you're experienced in differential equations, it's nothing crazy. So we're going to look at a couple standard examples and just the first, and then we'll work through basically what does the full workflow of an ODE modeling scenario look like. And then we'll talk about what I'm calling stock flow idioms. So these are things that as you're, if you're using this software to teach, you're going to really, you want to make notes of like, hey, this is a pattern that we're seeing. We can use this pattern repeatedly. And then we'll finish up at that point. We very well may be out of time at that point, and just come back and talk about like, okay, so where does this really again fit into teaching a first semester ODE class. Then if time permits, we might talk about parsing some files with Python and use, what is the categorical framework, which, again, at sometimes things like that seem like abstraction for its own sake, but I actually believe that it gives a framework to using this software for the faculty that tells you why it's different than just teaching, ODEs basically. So at the beginning, I want to just talk about like, hey, this is where I found out about Insightmaker. The first place I saw Insightmaker was in this book called Mathematics for Sustainability by Rowe et al. And this is a gen ed math class. So this is, that for that class, kind of quantitative reasoning class that students who are not STEM majors take to get their math that they're required to take in college done. And it focuses on sustainability issues. And honestly, I think it's a wonderful book. And the big idea, one of the big ideas in it, is that it just introduces stock flow modeling as a graphical representation of differential equations. It doesn't call them differential equations, and it never says the word derivative. It just kind of works with it as if, well, rate of change is something that is kind of familiar. And I think for the audience intended, it's avoiding algebra and equations is probably to some degree to not re-traumatize those students. And so I kind of read it and said, hey, this is a way to represent differential equations that's pretty novel, and should help students understand, even if they don't already know calculus. Well, it should also help students who do know calculus understand. And I think any of us who have taught differential equations know that there are issues with being able to do the procedures we want them to do versus actually understand what's happening. So that's how I came to Insightmaker. Just to always set up, when I talk about using Insightmaker in class, I say, hey, this is what my class looks like. If your class is for math majors with a linear algebra prerequisite, it's going to look different than mine. So this is a first semester differential equations class. We'd probably say it's really a sophomore level differential equations class. It has a second 2 semesters of single variable calculus. So if we're talking about the standard calculus sequence, it's differential and integral calculus, and then a bunch of sequences in series. I'm thinking about the roster that I have for differential equations next fall. I'm going to guess that 90% of the students in that are engineering majors. That's just one of the big majors at my school. The way I teach the class is definitely modeling focused. It's not, probably full in on semiode in the sense that it's not like we do a new scenario every day. There are days that are me talking and students not doing, not exploring as much. And that's partially cultural, that I don't know how well that would work with my particular student body. I use semiode scenarios or scenarios in the semiode textbook because of basically, equity and cost issues. I try to use all OER materials, but students, I tell them they should buy the textbook. I hold class in a computer, so this coming fall, I'm going to be having a class in a computer lab every day. So there's definitely a lot of technology used in the class. In the past, just because of space constraints, I've only been able to do it 1 day per week, but that 1 day per week would be the day that I have students working, doing things with Insightmaker. Okay, and then, so just to kind of set up how we're approaching this whole thing, I'm going to set up a dichotomy of ways students could come into a differential equations class, or things that they could get out of a differential equations class. The first is the student says a differential equation is a bunch of stuff with an equal sign. Solving one means applying some procedure according to how that equation looks. At the beginning, you do integrals for some reason, and then you quit. And the other part side of that dichotomy is a differential equation is a mathematical model relating changing quantities. Every symbol in a differential equation has a specific contextual meaning. Solving a differential equation means finding values of the changing quantities one way or another. I can do things that I'm interested in using differential equations. Now, clearly, I'm setting up a dichotomy because and the latter is preferred to the former. It's you know, so some, it maybe is not a fully honest thing to say that these are the two possibilities, but I'll say that I've interacted with math and engineering faculty whose attitude about differential equations is essentially outcome one. That it's just a class to get through and you do stuff and you don't know why. So I'm gonna say using Insightmaker is one of many possible ways that we try to achieve the second outcome here. Okay, so now we're going to get into what exactly Insightmaker is and how it works, and the basis for it is what's called stock flow modeling. And so stock flow modeling, so it goes by a number of different names. So it's system dynamics, stock flow, and in a lot of differential equations texts, it's called, you talk about compartmental models. They're all pretty much terms for the same thing. When we say stock, we're talking about some quantity that accumulates. And so this is why we use the word stock. And roughly the stocks are the dependent variables. In Insightmaker, there's something called a variable. Variables are parameters or other quantities occurring in a model. So you think coefficients that you vary somehow, or some sort of external force if you're talking about harmonic oscillators or something like that. The thing that I actually didn't put on this slide, which is really terrible, is I didn't say what a flow was. We'll see what flows are. They're flows between stocks or just into or out of a stock. And then there are these things called links that take you that they're pointers between stocks and flows and variables that allow you to use equations. These things, so links are a little bit of a graph theoretic or category theoretic construct. We'll see how they work when we start working through actual Insightmaker examples. The big formula, and this is the time derivative equals the sum of the inflows minus the sum of the outflows. This is something that you probably would tell every differential equations class you ever teach. Whether they fully appreciate how profound that equation is certainly debatable. Students start to appreciate it a lot more once you get into, using Insightmaker and building their own insights. Okay, so let's do an example. This is where you see the stock flow representation most frequently. If you do a Google search for SIR model, the thing that you'll get 1,000 different pictures of is essentially this SIR with little blobs and arrows, and you get the ASI and the KI. And that this represents this system of differential equations. The S prime is negative ASI. We're thinking, and we'll talk about, the meaning of these parameters. K is the per day percent that the infected people recover. A is some sort of parameter that measures the likelihood a susceptible person picks up the disease from an infected person on a given day. Okay, so let's look at this model in Insightmaker. And so now I'm gonna do a new share, and it's gonna show you briefly that, but so this is and sorry, I'm gonna back up just so we're gonna look at this board. So stop share, new share, go back to my slide. So the next slide is we're gonna explore this insight. This is using the modeling scenario in Simiode. And I'm gonna go back here. So the link to the modeling scenario, put this in the chat. Modeling scenario is here, and the insight on Insightmaker is here. And so if you want to go to that, feel free. The one thing that you won't be able to do is edit the insight. But and new share, actually get to that. So here is our insight. This is what it looks like. So we have S, I, and R. So S, I, and R are what are, so they are so-called primitives in Insightmaker. They are stocks. So if you want to add a primitive, you can go up here and say plus primitive and say add stock, add variable, add converter. We're going to talk about converters later. So S is a stock, and I give it an initial value. So that 763 initial value is the susceptible population in this boarding school according to the Simiode scenario. And there's some little toggles that you can have here. Allow negatives, conveyor. Most of the time with stocks, especially, so the conveyor is not something that you ever use in your ODEs class. Allow negatives, certainly if it's a population, you don't want to allow negatives. In a lot of situations, you do want to allow negatives. Position is, if the vector quantity, you can have negatives. The thing that down here, it says enable slider value for stocks. If you enable the slider value, that allows you to vary the initial condition with a slider. Scrolling down here, under validation, you can choose units. So everything in Insightmaker, you can assign a unit to. In this case, individuals is a common unit to use in Insightmaker. So SI, the initial value was 1. The units are individuals. R, nobody's recovered yet. The initial value was 0. Units are individuals. So those are our stocks. A and K up here in primitives, those are variables. Those I have as sliders, and notice so if I click on A, there's a value. I can deal with the slider. The units here are 1 over days times individuals. If you click on that, it tells, these are ways to assign units. I'm going to close this. We're just kind of going through what an insight looks like and what the components are right now. Those are the units of A. K is a % decay rate in the infected population, and it's going to be in 1/days. The time units you can choose up here in settings. I'm going to open that up. So settings, I chose days as my time units, and simulation start was 0, simulation length was 13. I chose that 13 because that's how long this epidemic in this boarding school was supposed to last, according to the Simiode scenario. And then the advanced settings are a time step and a simulation algorithm. The two that are available to you are Euler's method and RK4. If we have time, just if you want to use fancier algorithms, like if you want to use a stiff solver or just more accurate things, or you want to make them faster so that because you're not running it on a server, that's when, yeah, this is not perfect. You might want to import your differential equations into something else. I'm gonna hit cancel on that just because I don't want to change my settings. Then there are the flows. So the flows, you click on that, and this is where you get the flow rate. So the flow rate is given by ASI. Again, this is something where when you're teaching the class, you would say, what is the flow from S to I, and kind of develop this. Right now I have only positive flow rates toggled on because that's part of the model. If I toggle it off, and we'll see this in the simple examples, you notice now the arrow goes both ways and there's a little hollow point on one of them. That means that the positive flow is from the hollow point to the solid point. But I'm going to detoggle that. And again, we'll talk about why it can be very useful for students to kind of try to build their models only using positive flow rates if that's a sensible thing to do in that model. Sometimes the flow rate just can be negative. And then we have the same thing here. So we've got a KI. And so that means that the flow into R is a positive KI. The flow out of I is a negative KI because that's the direction the arrow is going. So I prime is ASI minus KI. So this is just a graphical representation with these two equations for the flows. This is just a graphical representation of that system of differential equations. And one thing, so what I've found in using this is that, yeah, students like having kind of both things because they see that, yes, the differential equation gets more contextual meaning with the graphical representation. And then finally, we can say simulate. So up here under, it says simulate. I'm going to hit simulate, and it graphs it for me. So I've got an SI and R. It graphed that. I can do different displays. If I say configure here, the default is, so I chose to graph those three primitives. So it's not often that you'd say, hey, let's graph the derivatives or graph the parameters. You can if you want. The other things that you can do is you can actually show a scatter plot. Then you have to get rid of one of those. The scatter plot would be a phase portrait. So you can only do a two-dimensional scatter plot. So you get something like that. So this is a phase portrait where you have I on one and S on the other. The other thing that's super useful in a lot of scenarios is, yeah, you can just actually look at the table. I'm gonna put the R back. I've got a table of values at every moment, and you can download that CSV and find the max or whatever you want to do. now I'm gonna go back to the time series because that's the one I'm interested in. This is a actually relatively new feature of Insightmaker. Up here it says sliders linked. And so this is actually pretty cool because one of the things that we want to always do is somehow match the solution to some sort of data. And the most primitive way to do that is, okay, play with the parameters until it looks right. So when the sliders are linked, I can actually move a slider and see what it does to the graph. So because you can do that just really dynamically, the students can kind of get a feel for what these parameters do without, I mean, I want to say without thinking too hard about it, but they can, if you just in class and they work with it and you say, okay, class, so what's going to happen if A increases? And you say, well, A is this transmission constant, so that means people get infected faster. So that means that the infected population should be steeper and it'll probably go higher. And then they can see that that was in fact the case. Or if the intuition isn't great, they can see what happens and then see, oh, that is not what happened. And likewise, if you increase K, so K is the rate at which infected people recover. So if I increase K, that should shorten the peak. And then we can say, does it shorten the peak and push the graph to the left or the right? I don't know if it shifts it left or right, actually, right? I mean, that's not super intuitive. And you see it, and it really just shifts it down primarily. If you wanted to see it really, whether it goes left or right, you might need to play with it more. But the ability to link the sliders is a really cool feature for students to really kind of experience what's going on here. All right. Does anybody have questions right now? Just or if there's something that, you know, hey, can it do this? I might be able to show you right now.
So Eric, that arrow in the bottom left in the blue circle is, if you start this, you'll see the graphs plot according to time.
Right. So I've got it. So there is the playback speed.
Okay.
I've got it at full speed right now, just because sometimes it goes real slow. If I run it at normal speed, then I can back it up. Then you can actually see it. Well, geez, let's do it at, 0.2 normal. Oh, it's really
You can pick it up anywhere you want, is what I'm saying.
right. So
Yeah.
you can back it up and see the time evolution of it. And the other thing, and one of the things that's kind of nice to do, especially with, so when you see the time series plot, it's a time series. So the horizontal axis tells you the time evolution. When you're looking at the scatter plot or the phase portrait, having the playback speed and be able to see it evolve over time is a very nice thing to be able to do. All right. Any other kind of blazing through? Well, I don't know if I'm blazing through actually. So I'm gonna come
So
up
Eric,
here.
Eric, I have another question. You
Sure.
talked about how having both the differential equations and the boxes, do you mix and match and sometimes introduce it with just the stocks and flows or differential equations? I mean, how?
So usually, I'm gonna get back to my slides.
Okay.
Usually I'd say I frequently I'd probably more often introduce, just, this goes back to sort of student psychology. Um, Equations and algebra are probably more in the comfort zone of the students. And so introducing with just here's a differential equation, and initially they say, okay, here's a differential equation, and now I'm gonna build the stock flow model from the explicit differential equation. At the beginning, that's something that that is more in their comfort zone. Probably later on, if I just say, here's a modeling scenario, they, I'll say, hey, try to build it just as a stock flow model initially, and then extract the differential equation model from that. So yeah, I do mix and match. And I'll, if we have time, and I really hope I'll probably try to fit it in if I can. Kind of what are the benefits of going, that there really is something more to the stock flow model than just, if the student can get the differential equation, that's it. So just as a, finish up on that, so this is a scenario that I might introduce like in the first week of a class. It gives the graphical representation of the model. These are like, last winter at the joint meetings, everybody does a COVID model, right? Every one of those COVID models is presented with some sort of stock flow diagram, practically. But the other thing that just having the students work with Insightmaker can do is there are units in dimensional analysis in that you can do with Insightmaker. And by the way, if we'll maybe stick this in there a little later, if you change the unit, if the units aren't right, Insightmaker, like as soon as you start using units, you gotta do it all the way through and make sure it's consistent, or Insightmaker will scream at you with some red box. So it does do validation on that model. So dimensional analysis is extremely important in development of the models, and it's something that you can really get students to internalize. You get those different graphical representations as time series, a phase portrait, or in table form really immediately. And because it's so easy to generate these things, the students can get a feel for what they tell you a lot more easily, I feel. And the other thing is that, the adjustment of sliders to sort of see what happens to solutions without dealing with all of the algebra is very helpful to students. And at this point in time, I'd say most of our students are probably coming from Desmos, right? They saw Desmos in high school. They've played with sliders before. And like, look, I think Desmos is great. I think slider math is quite a futuristic thing to work with. So these are just things that we can look at and illustrate just with this SIR model. Couple of remarks. The first one is you can leave everything unitless in Insightmaker and just say, I'm constructing this thing. I know what the units are on paper. I don't want to deal with it in Insightmaker. That's something that I've done in the past and I've not done in the past in teaching. There is a certain, right, and I say it's a battle you have to choose to fight. And what I mean by that is you need to be able to tell the students, like, hey, I want you to do this for a reason, and then you have to assess it. So when, and again, so just to back up on, I use the word assess. In terms of assessment in the class, I do have students turning in Insightmaker files of like, hey, this is, you know, I want you to demonstrate that you've gone through all of this so that you're really showing me that you've got this sort of novel understanding of the model beyond just here's an equation. And so the different representations and the adjustment of the parameters, like we all know that like, yeah, we're kind of trying to do data fitting. Yeah, both of these things we're gonna look at in a couple more examples. Okay, so the next scenario, and this one is I back up. The really, you know, like we see infectious disease modeling is where stock flow modeling gets used all the time. We don't see it a lot in other contexts within differential equations. Like you don't see it when you're talking about harmonic oscillators. One of the reasons that happens is when we talk about stocks and flows, you kind of often want to see flow from one stock to another stock. That's not a necessary thing. And so for instance, in a harmonic oscillator, you've got a position and a velocity, and position doesn't flow into velocity in any sort of direct way. There, you know, if you are shouting, but what about energy? Yes, that is, we can also gain some better understanding of why we talk about energy if you start talking about what's flowing into what in these physical models. But so what we can do is we have these things called partial flows. So the integrator, and now I'm going to again open up my browser and find my integrator and give you that in the chat here. So the integrator, I'm gonna go to a new share, open up my integrator. So this is the integrator. This is probably the most basic building block for doing insights. My inflow, I decided it was cosine of seconds. So seconds parenthesis is basically t. If your time unit is chosen to be seconds, if the inflow is cosine, then the function that should result, the stock, should end up being sine. What did I make my initial value for my stock? I made it 0, so I should get sine. And I simulate, and lo and behold, I get sine. If you change the initial condition, then obviously you change the initial condition. If you change the formula, you change the integral. The important thing, and this is where it becomes differential equations, is to change the flow rate so you can edit it in this box. But the other thing you can do, so I'm going to say expand there. I'm going to get rid of this. And the reference is big G. So if I say the inflow equals the function, I'm going to say apply. Now I'm going to change my initial value to 1. And I should get e to the x or e to the t. And well, in that window, it looks like e to the t. So this is our basic building block, and that builds off of what is called a partial flow. So you see that little cloud, that means that let me change this back to cosine. That means that there's no direct stuff flowing from somewhere into G. It's just that this is the flow rate. This is how stuff accumulates in G. The one thing, so I didn't have positive flow rates only toggled. If I toggle positive rates only on, and what's gonna happen now? Can anybody guess? Someone can speak up. What will our graph look like if I restrict to positive flow rates only, but the flow rate is cosine?
Anybody care to speak up? Live dangerously?
Live dangerously.
So you're saying instead of taking cosine, we only accept the positive parts of cosine as our inputs. Is that right?
Correct. So that we only integrate the positive parts of cosine.
Okay. So there's some lulls in the activity because you're negative
Yeah, there's
zero.
gonna be lulls in the activity, and it's never gonna decrease.
Oh,
So, so I'm gonna configure this to get my y-axis to go up to, let's go with y-axis up to like 10. Yeah,
okay.
so every time cosine is negative, it just zeroes out. So this is right, and at some point you might have students accidentally toggle that on when they shouldn't, and then they get something weird, and you say, what happened there? That turns out to be a really interesting feature to play with if you there are instances where you might want that to happen. So like if you wanted a different damping coefficient on your on an oscillator, so a different damping coefficient depending on which direction the thing is going in, that's something that you can actually cause that to happen based on using two different flows for different directions. So that's a really little interesting feature that's hard to implement with other software. So this is our basic building block, and we're gonna see a lot more examples, and many of the examples that are in a first ODE class, you're gonna see a lot of these flows they're partial flows in the sense, in graph theoretic terms, it's an arrow that doesn't have a source. In terms of if you said the stocks are sort of vertices on a graph. Okay, so I'm gonna go back to our slide, go back to the next example, and this is the one that I'm gonna say it gives us a full idea of kind of almost everything that Insightmaker can do. It's a good one to, like, I would say you might want to clone it, see how some of the things work in there. The modeling scenario, once again, open up my chat and put each of these things in. So the semiode scenario is here. So this is one about what are called ripcord toys. And the insight is going to be here. And then do all of you know what exactly a ripcord toy is? Maybe not. So in order to make sure we know what a ripcord toy is, this is what a ripcord toy is.
Now, you pull that T-stick, both FFP racers howl with power. Take that action. Crash them. Smash them. New SFP with Sonic Sound. Super Stalker. King Cobra. Detonator. Kenner's SFP racers for $72 now with sonic sound, each sold separately.
Stop that. Okay, that was enough of that. I can't imagine being a parent in the 1970s and getting to listen and buying a child those toys.
Incidentally, I keep teasing Brody, the author of this, of playing with toys on the floor instead of getting serious. But
Yeah, so yeah, Brody, I did not know. So I was like, hey, what is something? And Brody is actually someone that I know through my wife because she's in abstract harmonic analysis. And I was like, hey, that's actually a really cool scenario. So the ripcord toy is something, and I'm gonna make so everybody's seeing my slides right now, right? So it's this thing where you pull on the thing and it spins the wheel, and then you put it on the ground, and the wheel is gonna initially be skidding, and the skidding is putting a force onto this whole toy that then accelerates up until pure rolling is achieved. So once it stops skidding, the wheel is just rolling, then the velocity is just going to decay. So we have this model for the velocity, and this is just something that's given in the modeling scenario. If you really wanted to just do this kind of organically in Insightmaker, you would consider different things for different components of the model. And we'll see that we really do get to see the F and the minus KV and the different times that show up in the insight itself. So now I'm gonna get back to that insight. Okay. But this is the one that I want. And so right now you're seeing the whole model. Okay, so this is the whole workflow of the thing. There is this, so up in under share, there's this thing called storytelling. Within your class, you know, if you're someone who likes to have their students present things and say, hey, I'm going to show you how this works. Or I would say the storytelling feature might be really useful for someone doing the competition. What is the name of the competition? Sorry, Brian. The modeling competition.
Scoot 'em.
Scoot 'em. Right, this is something that, like, the storytelling feature might be super useful for a Scoot 'em student. Because you're trying to present something. So I'm just gonna say, start this story. So here's the story as we go. So we have, this is our model. We've got an acceleration and a resistance. The acceleration, so this F is the normalized force in the sense that we divide out by the mass of the little car, so that it really just is as an acceleration. If I look at this, the value that I gave it initially was 200, just based on kind of figuring stuff out. It is in centimeters per second squared. I chose centimeters because that was something that was given in the scenario. The T naught is based on data so this is one of the tables of data in the scenario. I say this T naught where pure rolling is achieved is around 0.7 seconds. Then there's this resistance term called K. I ballparked it at a 0.3, whatever, it's something. And now so the resistance term is just KV. This is an outflow, so I see that should be V prime is going to have a negative KV on it. In the acceleration term, click on that, and I'm actually just going to open up the expand. I can use conditional statements in the construction of a flow rate if I want. So this one was, so there's all sorts of different functions you can use. This one, I used it in the programming functions. There are some that you are never, that I don't imagine using. So there are like string functions and stuff. If you have some piecewise defined flow rate, you can use a conditional statement like this. One thing that I've found is some students, like, this is the first time they actually understand what a piecewise defined function is, because they've encountered if then else's in their first semester Python course, and they're like, hey, now, oh, great, I can use, coding syntax. So I want to undo that. Don't want to do another one of them. Some of the other functions that are available in the general functions, and there's pulse and step. If when you're introducing things like the Laplace transform, I think all of us probably encounter that the most difficult thing about Laplace transforms, it has nothing to do with Laplace transforms, but rather writing these shifting and stretching step functions around. This is a nice way that they can do it, and you can also start shortening the time that it's on and building yourself little delta functions and things like that. But this is a very cool feature that is just native to Insightmaker. So this is our velocity differential equation. And then it turns out that the data that's in the scenario, well, that's not velocity data. It's really hard to, observe a velocity. It's position data. And so if we want to build, compare to position data, we need to build a position function. And well, we have our little integrator, right? And so, and just by the way, anytime you see a link, in order to use that quantity in the flow rate, it has to be linked. So in this one, V is linked to the flow rate of S, and in fact, the flow rate of S's position, is just equal to V. And so this is just gonna say, hey, you find you have a differential equation for velocity, and you can then integrate that to get position. When students see something like this early on in the semester, if you just take that S and link it back to the derivative of V, now you've just got an honest to goodness second order equation. So this idea that the way you handle higher order equations is with systems of first order equations, it's super intuitive, which when you just introduce that idea algebraically, I've found a lot of students say this is confusing. Sometimes I say, no, it isn't, but it is to them. And so now we have velocity and position. And if I say simulate, I get this thing, and that break point was when I made that's where it changed the velocity. So you get these discontinuities or change the flow rate at that break point. There's this other graph here, the yellow one, that I'm calling data. Where is this data? So if and I haven't shown where the data is, our green graph for position isn't matching my yellow graph from the data very well. Okay, that means we need to slide the parameters around a little. If I increase the acceleration force, it's a little better, etc. I did it too much. Well, we don't, that's too small. I'm gonna ramp it back up to 200 just to have a good start point, about 200. the next step is, well, I can actually work with the data. So I have this thing called data. That's, so the little, I guess that's hexagonal. That's what's called a converter. So this gives you, you can take a table and put it in as a primitive. In this case, I took this data and there are inputs and outputs. This is from the scenario. It's one of the two data sets. There are different things that, so I can do linear interpolation, so that just draws a straight line between all of the points. Or you can do no interpolation. These are kind of up to you. I think linear interpolation probably makes some sense. The one thing that I'm going to say here is that there's an input source called frames, and I haven't said what frames is. These input values aren't times. In the table, it gives you the inputs are frame values, you know, how many frames per second. It's 30 frames per second. I had to create another variable called frames. Frames is just equal to seconds times 30. So that's what the input is in that first column. If I had chosen time instead, it would be different. From that, you can create the sum of squared errors. You take data minus S and square it. And notice that I have to, so because S was in centimeters and the output of data was in centimeters, the data minus S squared is in square centimeters. So this is, so at every data point, you get a squared error. Now, what do we do with this? Well, the thing that you always want to do is minimize the sum of squared errors. This is another super cool feature. Up here under tools, you can do optimization and goal seeking. I know that the T naught is about 0.7 seconds. I want to find the F and the K to minimize the integral of the squared errors. So really, I'm minimizing the sum of the squared errors. There are some so it's going to give you have a window of F and K values. Going to try to find this. It does some sort of it does an optimization algorithm. Some sort of least or gradient descent algorithm, I think, is what's in use here. I say run optimization, and we're gonna hope this runs reasonably fast. And sorry, we gotta wait 20 seconds or something. If you have a lot of, you know, different parameters and something that's hard to do, optimization may take a while.
And Eric, you fixed T naught.
I fixed T naught. If
Okay.
so I have run this where, so it is possible to do the optimization algorithm where you say T naught, F, and K are parameters to vary, and it'll try to do it that way. That's when the optimization problem starts getting really hard.
And that T naught was the time at which the spring had unwound, if you will, in the car, and it's on its own, basically, right?
So it's when the wheel stops skidding.
Oh, skidding. Okay.
Yeah, so and we've got another, you know, I don't know if I'll have time for it. Especially when so sometimes the I think the optimization might be running a little slow for me right now because there's a lot of things going on my computer with Zoom and such
Well,
running.
I know what's happening. It's self-conscious because we're talking about it.
That's actually quite possible. There we go. Okay, so now found the optimum where the F is about 224 and the K is about 0.235. And once it does this optimization, it actually resets those parameters to that value. Again, it's an optimization algorithm. It's not always going to be perfect. If you don't have a good initial guess, it may not find the one that you're looking for, etc. But the way we're going to check it now is do the simulation again. And you know what? The green graph and the yellow graph look pretty dang close together. So I'm going to believe that that is pretty close to the optimal solution. This is a little, all of these things are estimates, and then we're done with the story. It reset it. Let me close that. So because those are all estimates, yeah,
Can I
it's
just interrupt? I mean, this is rather remarkable because this is the full modeling cycle that you want students to see, from data collection through model through parameter estimation, all in one screen. It's remarkable.
that is, so I'm gonna just, now that we're done with that one, gonna bring up the next slide. Why is this so dang cool? Yeah, that's exactly it. I got to, I mean, this is something that depending on where, like, I would probably not put the you know, maybe not do that model in the first week because it's piecewise and all that. Maybe choose something different, but you can see the complete workflow of the model on one screen, right? And just and that there's not a bunch of I got bogged down in solving the differential equation analytically, and then I got bogged down in trying to use Excel to do something, and then I got bogged down, right? It's one screen. The student sees the full workflow of how this works immediately. And even that, when they look at that differential equation, they're seeing the inflows and outflows broken into meaningful pieces. And the other thing, I mean, I kind of do point out that students, my students at least, often have difficult times with things like system, you know, like one differential equation, they're like, okay. But then just the idea of turning everything in the universe into a system, they in the past have resisted, whereas with Insightmaker, they're just like, well, of course. I mean, I ask them, okay, if we're doing a second order equation, how many stocks are we going to have, without ever telling them? And they say, well, we're going to have 2 stocks. And so we get that entire thing all at once. And the other thing about the formulas that I'm going to come back to again is the fact that we used like an if-then conditional statement in the formula, or if we use a step function syntax, that's something that in kind of the modern curriculum for a lot of engineering majors, like at my school, the intro Python course is kind of taking over as that's the bigger gateway course than calculus. These, students are finding interacting with technology in modern ways like that, in coding ways, very natural these days. And so that's something that when we enter those formulas, the fact that we can do it in kind of a codey way is very nice. All right. So now I'm just going to go through some of these things that I call stock flow idioms. I'm always really explicit that these are things that, when we notice that this is some sort of piece of a diagram that we use repeatedly, I make it explicit. I tell the students like, hey, remember that this is something that you can do. The single stock ODE, you've got a stock, you've got inflows and outflows, and you've got different parameters. When I'm writing that as just I'm using plurals on inflows and outflows. You can have a bunch of different inflows and outflows associated to possibly different parameters. Some of those parameters need to get linked to both. Sometimes, so this one is just very generic, so I didn't restrict flow rates to positive only. Sometimes it's really semantically meaningful to restrict to positive only. Another one is higher order equations. So kind of within, obviously each one of these might have a more fine breakdown into inflows and outflows, but this is what a higher order equation looks like. This is representing that higher order equation as a system of first order equations. Again, I say this, so if you say, hey, I want an external force somewhere, you can actually add those external forces, like a forcing function is something that you can make into a variable and link it to the equation. The other idiom that I use a lot, so if you have systems, and this one is kind of interesting. So if you have variables that really interact with one another, you get these links going between all of the stock flow pairs, basically. So going from a second order equation to just a two-dimensional system or a three-dimensional system, they just say, oh, I just have one more link, right? The thing that is interesting, a lot of our students probably are learning a little graph theory here. I don't know if this would be an interesting little research project for a student, but what are the, if we kind of identify stock flows into single vertices, you get, the completeness of this graph, or, what are the kind of graph theoretic properties that, and how do they translate into differential equations properties would be kind of interesting to talk about. And then the other just kind of the other idiom that gets used a lot is that data, how do you estimate parameters from data? And that's less of a stock flow idiom than an Insightmaker idiom. You use that very frequently. Back to the slides. And so just, I think I'm kind of coming to a halfway reasonable stopping point. We're not gonna talk about category theory today, I don't think. Oh, I forgot about the conserved sum. This is the one that actually is present in the SIR model. If you have a string of stocks and just two directional flows going between them, that's a nice way of saying, yeah, we've got that the sum of these variables is conserved. Another kind of application of that where it's present, back to, is, so I have a different version of the ripcord toy scenario, which I'm going to put in the chat, where it uses a conserved energy. So we actually have the energy of the wheel and the energy of the car. So it's the kinetic energy of a wheel and a kinetic energy of the translate. So rotational kinetic energy and translational kinetic energy, and you can actually think about like, okay, what's, you know, how is this energy transfer from wheel to car actually working? And I'm gonna say, if I simulate this, and it goes. So this is a conserved energy problem. The sum of these two is constant, and it has that breakpoint, which I didn't have T naught as a parameter. You can, it's not that difficult to work out what happens in terms of the energies when the pure rolling is achieved. So that's another one. So all right, and then finally, just going back to my slides here, I'm gonna say, here's just a little bit of things that you can do just to kind of try to experiment with Insightmaker on your own and think about how would I use this in a class. In that original the SIR model semiote scenario, there's data, right? This is one of the sort of original published SIR modeling data sets from the boarding school in England. That, yeah, take that data and build yourself that right, you can, so all of those insights that I put up are public. Think about, right, try to build a converter and do the optimization problem to estimate the parameters for that. And then the other thing that I would encourage you to do to just sort of get an idea of how you might have students working with this is on that SIR model, say, okay, so let's say on one of the days, I think 3 is fine, you somehow manage to be able to isolate all the susceptible students from all of the infected students. How would you implement that just in the insight? You can think about how you would implement it in the differential equation. That's easy enough. But I would say, yeah, do it with Insightmaker so that you can really see what would happen. And then the other thing is, you know, how would you what would you add to the insight to account for starting to vaccinate some population, you know, some percentage of the susceptible population each day? I think if you kind of work through these, you'll probably get a pretty good feel for how you could have students working through scenarios with Insightmaker. All right, I'm gonna kind of stop right now and ask if anybody's got a question. Because otherwise I'm just gonna pound forward and do other stuff.
You mentioned that things were public.
Yes, so
Okay. Public means at Insightmaker, and how would I find your SIR model, for example?
so how would you, so I'll go back and share.
I mean, you've given us the link, but I'm just saying, can you wander around inside?
Yes, so I'm gonna come here. So every insight, so in the info, you can say edit info. And one of the things that I will encourage you to do, if you're creating a lot of these and using them with your students, I'm gonna say you might want to make your own that are solutions to your assignments private. I made these public. So if you want to look around, if you just, so I'm gonna go home here. And so if you say explore insights, can you find mine?
Well, by the way, the titles that I can see on that screen are exciting enough. I mean, I'm going to forget yours and look at these.
Yeah, so I mean, and there are a lot of insights, and some of them are really complicated. I mean, like, here is an insight for the economy of the United States. You're going to be able to find that. These are gigantic diagrams. If you
But for example, I'm thinking about just having a little unit on delay differential equations. So I see that word down there and I'd look into that. Maybe it is, maybe it isn't good, but it allows. And then once you get to that topic, it breaks out all of these that someone has developed.
Right, and the other thing that so I think if you find something that's been, right, if you know the author, you can find all of their insights.
Okay.
All of their public insights, at least.
Yes.
And so kind of the other thing that I feel like I want to point out, I'm going to go back to home. So these are my insights. And so, like, the seasonal predator prey model, right? This one is public as well. This one is one that you might, this is the one that I was going to talk about, why you might want to pull things into Python. And it's because for one of so you can make scenarios based on sets of parameters. If I simulate that, and this one is pretty slow because it's a really long simulation, you can, so when you share these things, you can actually download what's called an Insightmaker file. Those are what I use to, like, if you want to keep things really private or have the students turn things in and there's privacy issues, I have my students turn in an Insightmaker file. I can open that Insightmaker file on Insightmaker, and then delete it, right? So that the students don't have to have stuff published.
So those are good lessons for management. And I think that's important, that the students feel comfortable with privacy.
And I'm going to do one more thing with this one because I think it's really cool. So that this is a feature that you can do. I'm going to change. So the S and M are snakes and mongooses, by the way. I'm going to run it like that. So I changed the initial value of one of my variables by 0.01. And you can do up here in tools, you can say compare, and I've got those two open. And I'm going to just look at my snake populations and compare. And this is one of the like, hey, I get to actually, students get to see how sensitive dependence on initial conditions really works. Where, oh yeah, they start out really well synced and then they go completely out of sync at various times. So that results comparison table is actually pretty cool. All right, so
one other thing you talked
think
about
France has a question.
Oh, good.
Hi. Oh, thanks a lot for a very good presentation. I'm a fan of Insightmaker myself, and I did learn some things with the optimization. I never thought of using it that way. I was happy to see that we had something in the wiki models that we saw the other day, but we have the equivalent now in Insightmaker. there, and you've shown quite a large array of all the possibilities. I might just add the two things. There's also sensitivity testing, where you can have some variables be random variables, and you can see the spread of the curves using that feature. And for the conserved sum, which I thought was a nice idiom that you introduced, I think there's also in the graphical representation, where you can use, they call this the area representation, and you kind of see they superimpose the value of the variables one on top of each other, and you can see the sum being constant. So that's
Right.
another way.
Yeah, so that's I mean, and that's one that I don't typically use because it's right. I mean, my students they're coming from a calculus class.
Yeah, they can mix it with the integrals. I don't like this idea of the area, but it kind of makes sense
Right,
in a way.
especially for that conserved sum, because you see that there's these two things and they take up the same area for the whole time.
Big rectangles, basically.
Yeah.
But my question would be, like at first you mentioned of this novel approach, and it's been there, maybe not in Insightmaker, but like Stella software has been there from the early 80s, and it has struggled to catch up or to be used on a general on a broader base. Where in your institution and your college, are you the only one doing that? Is there a group effort? And what would you explain the slowliness of the whole system to you
So at my institution, I'm lucky in the sense that, first of all, my wife is also one of the faculty here, so I can force feed her Insightmaker. So she's used it also. And I've got another colleague who is kind of game to do crazy things that Erich wants to do. So at my institution, I've got I can get buy-in. The why it doesn't get wide use, you know, I'm gonna say that part of that is it's that oftentimes mathematicians will kind of confuse conventional notation with rigor. Which I say, especially as we scream through the 21st century, we probably need to stop doing that. But the idea that, well, it's real differential equations if you write them down like Laplace did, versus this is right. The stock flow models, that is the differential equation. It's not something different. It's just a different way of writing it. And the other thing, and this is something that I'm gonna say I've got, a month to take care of, is there aren't great resources for teaching out there. And so the thing that I'm working on right now is writing some sort of it's going to be an open source pretext, like a supplement for a differential equations course for using Insightmaker in the traditional differential equations course. These things get used a lot outside of differential equations. It's the most bizarre thing. But creating those resources for faculty and for students, one of the issues that kind of happens is that a student will say, but I don't know how to use Insightmaker. And I say, well, you're right. I mean, the flippant thing to say to the student is, well, there's just a manual, let's read it. But there isn't something that's in a textbook, right? They can't take a class on this. So having some sort of resources of usage at a really basic level for inexperienced modelers and people who are new to differential equations is something that doesn't exist right now. And I think with Brian, I think of two or 3 years ago, I gave a talk about this at the joint meetings, and we set up an Insightmaker group in QBs, and I think it didn't go anywhere because I was busy being department chair, and it just doesn't get advertised enough. And I think I'm gonna try to kind of reinstitute that and maybe get some of these resources out there publicly so that it isn't something where, you know, McAlister says, oh, go play with Insightmaker and use it. Well, that's a lot to ask of someone. So one of the reasons I think it doesn't get used as much as I think it should get used is just the lack of publicly available teaching materials.
Yeah, and just a quick question. Thank you very much for this complete answer. Another question. What room do you leave for numerical methods in that first ODE course? Because I think unless you open that black box, which is at least the Euler one.
So this is where and I had a little concluding slide of how does this fit into the grand scheme of my class. Because I'm still a service, the class is still a service class for other departments. We definitely do, so as far as I go with numerical methods is Euler's method. And then you tell students that if you're using, you know, that RK4 is fancy Euler's method. And most of the engineers take a numerical methods, they take a numerical analysis class later where they dive into it more, presumably. So we definitely do some do Euler's method, see how that works in a day or two of class. And the other thing is that one thing about, you know, Insightmaker is that you don't do anything analytic with it. But analytic methods are still certainly present. And one of the things that I do quite a bit is use Insightmaker to support the analytic methods and vice versa, where something might be, okay, so we find this solution analytically, we plot it with Insightmaker and notice that, oh yeah, the parameter, it's behaving the way it's supposed to. And then I'll always say, oh, now change this in that model. So the for instance that I would give is in the Semio textbook, there's an air spring oscillator model, which they learn how to do an oscillator. And then you say, okay, so what if it's a nonlinear spring? You can't do it analytically. And then so you say, okay, you linearize it and compare. So you get these things that can support each other with the analytic methods and the numerical methods. Those are all components of the class.
And do you sometimes, and that's the final question, promise, you start with because analytical methods, you will hit a wall where you can't solve a more complex model with that. So you start with a simple model that can be solved analytically, and then you build on it and then have Insightmaker handle the rest of it.
Yeah, exactly. I mean, that's another part of the workflow of working with differential equations is that you've got the simple things that you can solve exactly, and then you modify it by that much and all analytic methods fail.
It's chaotic on its own though. Okay, thank you.
So do we have any other questions or comments? We can linger a little longer. Any other ideas that you wish to engage in?
And one thing I'll put out there is like, I could go on about this for another 2 hours probably. If anyone wants to just like shoot me an email, I'll send you other things and other resources. And also I asked if we can post the slides that have some extra links in them that I think are also useful.
Yeah, we
Yeah, I think William's got a question.
yeah, William.
Yeah, thank you. I think this was a really interesting talk. And I'm thinking about using some of this in my OD class in the fall. How long would you say it takes to get up to speed on Insightmaker to be able to develop things to use?
Honestly, I think so do you mean from the faculty point of view or the student point of view? Faculty, I think if you take that like it's an hour investment to get up to the point where you're ahead of your students. Like if you've got if you know differential equations, you will start in on it really fast and be like, oh, this is actually pretty cool. And is once the thing that I'll encourage you to do if you start using this is you can always build your differential equation as just like there's a stalk and one arrow, right? And just because everybody's hanging around, I'm going to share one more slide that was much later. So this is where there is the category theoretic terms. We've got isomorphism classes of stop flow models. So this is like populate, a logistic growth with harvesting. I can glom everything into one flow and put that whole formula into that one flow, or I can use 3 different flows. In the category theoretic terms, these are non-isomorphic. They're representations of the same differential equation, but they're different stock flow diagrams. And one of them, you get to see all the 3 different ways that things are going on. That's, try to, kind of get into the practice and have your students get into the practice of this is how these things are actually working. But once you do that, that's where you'll start to feel like this is something different than just doing differential equations.
Question of Lee, are these chats stored so that participants can see that at the site?
They'll be here on the Zoom platform, but unless we do take some action, they won't be on the YouTube.
Okay,
It wouldn't normally be on YouTube. We would have to do something special.
so one of the things yes, Eric?
So all of my slides, so every link that I shared is somewhere in the slides.
Great, okay. So we will work on posting the slides in a convenient place with pointers from inside Simiode. And now I want you all to be sure to turn off your mics, turn on your audio. Let's all do that. Come on now. I used to teach at West Point and I would normally order people to do that, but I want you to unmute yourselves. And I want us all to give Eric a big round of applause and appreciation. Okay. I personally want to thank Eric because I learned what a quality teacher is. As I watched this presentation, I saw the flow that you've offered and the sort of the style of giving us little teasers about what you could do and then fulfilling that throughout it. So we really very much appreciate this. And I'm going to stop the recording. And if we want, we can stay and linger. Thank you very much, Eric.
You're all very welcome. I'm really happy for this.